And again, I don't have to redo a lot of this just because she talked a bunch about it. But as we look at our confidence interval for proportions is what we're focusing in on. A point estimate is the value of a statistic that estimates the value of a parameter. Now, a point estimate in our case over the next 2 units, our point estimate is either going to be, in our case right now, p hat. Our point estimate is going to be p hat is what our value is. Give me a second. I'm trying to get my pen to cooperate again. So that's the point estimate we're using right now is p hat. Later on, when we do this in 2 weeks, our point estimate is going to be x bar. And that's when we're dealing with means. So right now, our point estimated, we're going to be using p hat is what our point estimate is. Since we don't know what, for most cases, the true population proportion is, we use a confidence interval to estimate a range of values where we think it should be or may be located. Because again, when we think about the gummy worm factory, can they weigh every single bag and to get the whole population of the stuff produced that day and figure out, okay, are we okay? The challenge is if they do that, if they decide they're going to weigh every bag, they're going to slow down production. They're not going to get stuff shipped out, which means there's going to be shortages out there in the stores, and which is going to hurt them financially. So that's why they do a simple random sample of periodically of bags, and they say, okay, are we okay when we weigh these? Here are the conditions that need to be met before determining a confidence interval. First, the data needs to come from a simple random sample or a randomized experiment where we randomize maybe the assignment to like the placebo and a drug as we're doing an experiment. Do we have some randomized experiment going on? We have to do the approximately normal again, where n times p times 1 minus p is greater than or equal to 10. Again, we're dealing with proportions, so that is our condition that we check when we're dealing with proportions. The n is greater than 30 is for means only, so you want to make sure that you're careful. And then independent. Since sample without replacement, we need to make sure that our sample size, which is lowercase n, is less than or equal to 0.05 times the population. Or the other way is 5, again, my pen's being stubborn, is 5 times little n, is it less than the population? So a confidence interval, again, we have different percentages. You can technically do any one, as she talked about it, any type of confidence interval that you want. Basically, the most common ones are a 90%, a 95, and a 99% confidence interval. They're most common ones that are used. 95 is probably the most common because in a court of law, as we look at hypothesis testing the next couple of days, a 5% alpha, and that's what that Greek letter you see there, alpha. A 5% alpha is what's acceptable for a court of law as they're making justifications. Is it, is this thing just a random occurrence or does it happen more frequently? So that's why a 95% confidence interval is the most common one that's asked to be done. The challenge is, as she was mentioning, the higher the confidence interval level, the wider the interval, which, again, as we're trying to make decisions about the greater population, it makes it tough. Whereas if you have it too low, then you have a really narrow area, which makes it even challenging on that side. So trying to find the nice, happy part, is what you try to do. That's why 95 is used the most common because it's kind of that happy medium out there for looking at it. So as I have this next one little setup here, is basically, and she showed a graph of this. If I did a 95% confidence interval, so as I try to get this thing to cooperate, 95%. So when you do a 95% confidence interval, we want 95% of the data, basically is in the inside, which leaves about 2.5% on the outside edges. We usually see margin of error sometimes when we do elections. they'll do polls and they'll say that, hey, this candidate has this percent of the vote or support with a plus or minus so much margin of error. And so the percentage they tell you is the point estimate, and then the margin of error kind of tells you the upper and lower bounds of your confidence interval is what they're giving you. If I do a 90% confidence interval, again, my area in the inside shrinks, gets closer together, so there's where my 90%. So the area where I think the true proportion is in the middle there, but now that puts about 5% in the outside sections, is what that does. So as you lower the confidence interval percentage, you make the width of your interval smaller. So the lower and upper bounds of your confidence interval get closer and closer together. If you do a larger, like a 99% confidence interval, then that means we have a wider interval. There's 99% in here, which leaves basically 0.05, or not 0.5. It's 1% on the outside, so it'd be 0.5%. 0.5% is on the outsides. And that's where she was mentioning that, we could go a lot further and get a 100% confidence interval. The only fortunate thing is that basically means that my numbers for my interval are so far apart. Yeah, it's going to capture the true proportion of the population, but it really doesn't help me for making decisions, especially when I'm looking at maybe these things being on a financial aspect for a corporation. Does it make sense? Again, that's just kind of give you a picture representation of what happens to your upper and lower bounds. Again, the lower bound is what's on the left-hand side. Lower bound, upper bound, lower bound, upper bound. Again, as the percentage increases, the lower and upper bound get further apart. As our confidence level percentage decreases, they get closer together. So again, she did a quick little thing about talking about, well, what is a 95% confident interval? What does it mean? Well, here we have basically 100 samples over here and another 100 samples over here. And again, they couldn't do it in one graphic. So it was in a total of 200 samples in this picture representation, 100 and 100 put together in this situation. About 190 of them, that's the green, 190 of them actually contain the P, which is the 0.7. Those are the ones that actually contain it in some form or fashion. Sometimes it's dead center of the green interval. Sometimes it's not. It's off to the little edge. But basically the red bars that we see on our graph, those are samples where they did a random sample and the confidence interval did not include the population mean. So there was 10 examples up there of when that the population mean was not included inside the confidence interval. And that's what the 95% confidence interval is telling us is, hey, 190 of them should contain the true population mean. About, in this case, 10 of the intervals don't contain it. Now, here is the handwritten formula for calculating a confidence interval with proportions. What we do is we take our point estimate, p hat, do plus or minus whatever our z star is, and we're going to talk about our z star. It's known as the critical value. That's our little critical value. And I don't know if you remember when we were doing our z-scores and percentiles, we use that table, or we use the inverse norm to figure out what is your z-score associated with an area to the left of a certain amount. So we get to use the inverse norm to help us figure out what that z-star is based on our confidence interval, and we're going to walk you through a couple processes of how to do that by hand. A lot of the time, since it's like usually a 90 or 95 or 99% confidence interval used, usually you can memorize those three different z-stars and you're good to go when you're looking at a time situation. You know, but again, we're going to show you how to do it for any confidence interval they ask you to do. Like if they ask you to do a 84% confidence interval, we'll show you how to figure out what is the Z-star associated with it. What we have to do as we, you know, on our confidence interval, our P hat is in the middle, right where the mean is. There's our P hat. And then to find each of the little borders, the upper and lower bounds, as we look at our upper bound and our lower bound, what we have to do is to find our little Z-stars, this Z alpha divided by 2, and then we figure out, and then we multiply it by the standard deviation of the P hat, and then subtract it from whatever your P value is there. On the piece of paper of the table, these are the right here. These are the Z stars. This critical value, this Z star. Those are the Z stars associated with these types of confidence intervals. So, you know, that's where I was mentioning where, since those are the most common ones used, instead of doing an inverse norm, you could actually memorize those 3 sets of decimals and use those decimals for your Z star, since those are the most commonly one used. Again, we're going to get practice here in a moment of doing that. I put a little side note over here. When we talk about confidence intervals, as the confidence level increases, the margin of error gets larger, and therefore the confidence interval gets wider. If the sample size N increases, the margin of error gets smaller, and therefore the confidence interval gets narrower. So we get closer together for the upper and lower bounds. And I know I'm going quick through this part. It's mainly trying to get to the practice of doing these things as we go. Here's an interpretation when you get done with doing the confidence interval. We go through and we describe, you know, hey, we are blank % confident that the interval, give the upper and lower bound, contains the true population proportion of whatever we're dealing with in our problem. And I'm going to walk you through a couple of those here in a little bit of how we write that conclusion statement. And then I'm not going to do too many by this setup right here. Again, I would write that on your little cheat sheet notes for the final, is having that formula set up for confidence interval for proportion. So I would definitely, you know, label that, you know, confidence interval, C interval for proportions. I would write that down there and have that there. That way, in case you have any multiple choice questions on your final, to where, hey, I just need to know the setup of it. But and that's what the AP has. They have some multiple choice questions over the true setup of the confidence interval in that format. So that's my recommendation of why to put it on your, to make a little note to put that on your little cheat sheet for the final, to make things go a little bit quicker if you can. We're going to use the TI-84 to figure out what is the confidence interval, what are the lower and upper bounds. To get to the interval, we go in and we press stat, arrow to the right, and hit the test column. And then we scroll down till we see a 1 prop Z interval. So real quick, I want to show you that on a calculator. If you need to go grab one of mine, please go grab one. But I want to show you kind of what that looks like on the screen before we actually do stuff. So any of our confidence intervals, any of our test stuff is in the stat feature of the calculator. So if you press the stat button, arrow over to the test column, anything that has the word test after it is a hypothesis test. Right now, today, we're doing an interval, is what we're doing. Tomorrow, we're going to be doing a hypothesis test. So that's where we're going to be using option, let's see, tomorrow we will be using option 5, a 1 prop Z test. That's what we're going to be using tomorrow. For a 1 prop Z interval, it's actually on the next page. If I scroll down, And there is my option A, a one prop Z interval. So as we go to do stuff today mathematically to find these intervals using the technology, that's where we're going to help to go through and have to type in stuff. And as I wrote down in step number 4, if we press enter, all you have to type in is, okay, what is the X value? What is N, which is your total sample size? And then what type of confidence level are you doing? Those are the 3 things you need to do. The confidence level always needs to be a decimal. Okay, so if it says 99%, you got to put in 0.99. If you put in 99, it's going to give you an error. It's got to be a decimal. Okay. I'm going to go ahead and quit and get out of there, because we'll walk through that in a moment. And so here I just have you guys practicing in this first part is to construct a confidence interval of the population proportion with the given its confidence level. So this is actually doing this part right here. It's doing that part right there just to get the confidence interval. We're not worried about interpreting. I just want you to practice that calculator command of getting those things in there. So we are doing a one prop for proportion is what prop stands for. One prop Z interval. And we're going to have to type in what is the X value, which is 30. What is the N value, which is 150. Usually we have to pull it out of word problems. And our C level is 0.90. So just to give us practice finding that, we go in, we press stat, go over to test, down to option A, one prop Z interval. Our X value is 30, our N is 150, and our confidence level is 90, so 0.90. And then I hit enter. And so the lower and upper bound for this one, our confidence interval is from 0.146, or sorry, my pen keeps having quirky times. 4628, comma, 0.25372. Again, don't worry about rounding those. I would just write that down as your confidence interval. Don't worry about rounding it to a certain decimal place. That's enough to be able to decide on a multiple choice what you're doing. And for when, I know I mix up multiple choice and not, write that down the way you see it, because that's the way I write it down when I put it on there. Notice they give me the p hat. If you notice the second line down, it says p hat for this problem. The p hat is equal to 0.2. They got that by doing 30 divided by 150. That's actually how you get the p hat there. 30 over 150 is 1/5, which is 0.2. So the calculator actually tells you what the p hat is. It tells you what the point estimate is. And so, again, we can all work at different speeds. If you can go through and find the interval for each of the next 3 just to keep practicing. Again, I'm doing a one prop Z interval. And again, my X is 80, my N is 200, and then my C level is 0.98. So that's my calculator command. And then we just go ahead and do it. So stat over, oh my fat fingers. All right, so now 80, 200, 0.98. So on here, my confidence interval would be would be 0.31941, comma 0.48059. Now, since we changed our values of the X and the N and the confidence level, we cannot compare the two answers we just got to say, hey, what happened as I increased the confidence interval amount, because I'm not dealing with the same information of the X and the N. So if you really want to tell, how does the confidence percentage change the interval, you got to keep the same X and N in your problem as you see that it gets wider and gets smaller as your interval. Well, let's do one. We'll do one more because I want to make sure I get into all this stuff that we're doing here. So stat that there. And here we got 120. I'm just going to hold off writing down the calculator command on the paper to save time. 0.99. So here my interval for this one is sorry, I apologize. My pen acts squirrely times. So there's my upper and lower bound for my confidence interval. And again, the last one, if I do it real fast, all right, we got 400, 1,200, and then 95%. And that gives me 0.30666 to 0.36001. All right, next part. Next part, they asked me to go through. They tell me the upper and lower bounds. So they tell me that my confidence interval technically is 0. So they tell me my, come on, pen. So that's my confidence interval. They asked me to go through and figure out, okay, what is the point estimate? What is the PE for point estimate? What is the margin of error is what they asked me to do. And then they asked me to find the number of individuals, X, based on the sample size provided. So we got three answers here. So what is the X value is what they're asking us for. Because we know the N is equal to 1,200. So when they give you the confidence interval and they want you to find the point estimate, all you have to do is take the lower bound plus the upper bound and divide it by 2. The point estimate, no matter what type of confidence interval you're dealing with, the point estimate is always at the dead center of your confidence interval. So in a way, it's like the average of the upper and lower bound. Doesn't matter for proportions, doesn't matter for means when we do it in 2 weeks, when we change the next part. If they ask for the point estimate and all they give you is the upper and lower bound, add the two numbers and divide by 2. And then I'll tell you what your point estimate is. Because it's always in the dead center of the confidence interval. So in our case here, we would say 0.201 plus 0.249 divided by 2. So let me grab my handy-dandy calculator. 0.201 plus 0.249 divided by 2. And I get my point estimate is 0.225. There's my point estimate. I would always go back and double check, is 225 between 201 and 249? Yes, it is. It should be in the dead center of it. My margin of error is actually just the difference between the two and divided by 2. So it's the upper bound. Now, order matters in subtraction, so it's upper bound minus lower bound divided by 2. That tells me what my margin of error is. Margin of error is the amount from the center, the point estimate, out to the outside edges. So here, what I can do is take my upper and lower bounds and subtract them and divide by 2, and that tells me the margin of error. So in this case, we would say, okay, what is 249 minus 201 divided by 2? Well, that would be 0.048 divided by 2, which is 0.024. So my margin of error for this problem, my margin of error is 0.024. 0.024, or about 2.4%. And then the last thing they asked us to do in this part is to figure out, well, what is the X value based on the information given if we have a sample size of 1,200? Well, this is where we got to remember that P hat is X divided by N. Now, we found P hat. That's our point estimate. Our point estimate here, our point estimate, our PE, that's the P hat. So we know that 0.225 is equal to X divided by 1,200. And then now all I need to do is solve for what X is. So inverse operations, if we multiply both sides by 1,200, and we go 1,200 times 0.225, I find out that X is equal to 270. So in that sample of 1,200, whatever the scenario is, 227 of them, or 270 of them met the criteria of whatever it was. Whatever the situation was, word problem was. And again, we get to practice that a couple more times. So lower bound is 0.0051, upper bound is 0.074. I'm going to find my point estimate first, which is P hat. So I'm going to write down that P hat, my point estimate, my PE, which happens to be P hat, is going to be 0.074 plus 0.051 divided by 2. Which works out to be 0.0625. And then for my margin of error, that is just the subtraction between those two things divided by 2. So 0.074 minus 0.051 divided by 2. And that is come on, baby. Come on. We're doing so good. 0.0115. So that's my margin of error. And then the last thing they want us to do, as I try to separate my work here, they want us to figure out what the X value is. So here, P hat is equal to X divided by N. So our point estimate of 0.0625 equals X divided by, what was our sample size? 1120. So then X is equal to whatever 1120 times 0.0625. So 1120 times 0.0625. And X is equal to 70. Now I'm going to pause for a second. Are there any questions on trying to calculate the point estimate, the margin of error, or the X value since we know the P hat and the sample size? Does anybody have any questions on those? Now, this same technique that we're doing right now, we can do with means later on in a couple weeks when we change it to be X bars and that kind of stuff. So it doesn't matter what you're doing. You get to find the point estimate. You always add the upper and lower bounds divided by 2. Find the margin of error. The quickest way is subtract and divide by 2. Now there's other ways. You can actually go find the point estimate and then say, okay, what's the upper bound minus the point estimate? That's my margin of error. So there's several different ways you can do it. I just think it's easier using one fraction and knowing that the point estimate means I add the two things and divide by 2. And then the margin of error is just subtract the two things and divide by 2. That's just a faster way to A is one thing, just change the sign in the middle, and that gives me my two values. All right, so that should get you through some of your homework problems. The next part, they asked us to find, okay, what is the critical value? So this is the Z-star. So this little portion right here asks you to figure out the Z-star associated with each of these confidence intervals, so the little Z-star there. So since we're dealing with Z's, and again, it was hard to type this in the calculator, this is our Z alpha divided by 2, is what that looked like on the little graph up above in the notes. So that's what that was supposed to look like. I just couldn't get it to be a subscript really good, to have it drop down. So I think one of the easier ways to do this portion is, since we're doing a Z, that means I do an inverse norm. So I do an inverse norm, because Z stands for Z scores or standardized. So inverse norm. My area is 1 minus my confidence interval divided by 2. So whatever that works out to be. And then now my mean and my standard deviation. Going back to some earlier units that we tackled with the inverse norm. If it is standardized, what is the mean and the standard deviation always? If you standardize something. If you had a standardized normal curve. Does anybody remember? What'd you say?
0 and 1.
Yes, ma'am. 0 and 1. The mean is 0 and the standard deviation is 1. Again, when you're dealing with the letter Z here, this Z stuff, the Z stars, that means it's been standardized. That means we have a standard normal bell-shaped curve, which means the mean is always 0 and the standard deviation is always 1. So now I get to go to the calculator. So I'm just going to simplify this little part in here. 0.90 divided by, actually, hold on a second. Yeah, 0.90 divided by 2 is 0.45. Well, I don't like that. Hold on a second. That's not, because technically what's supposed to be, if I draw a picture, this is where my brain's, if I have 90% in the middle, that means there's 5% or 0.05 out here and there. And so as I want to find my Z-star, I can say that that's 95% is to the left. Yeah, I don't want to do that. Oh, okay, yeah. Well, let's change that. Let's make this, let's do this. 1 minus 0.90 over 2. Let's do that, because that's what this number is right there. So that would be 1 minus 0.90 would be 0.10 divided by 2 is 0.05. So we're going to find this Z-star right there. So we're going to put 0.05 in for the area. And so as I get to my calculator, remember inverse norm is above the variables. It's a distribution, so second vars, option number 3. My area is 0.05. My mean is 0. My standard deviation is 1. I have it set up for a left tail, and so I would leave that alone and then hit enter and hit paste. And that gives me, for that Z-star, as I go way out here, that Z-star is equal to 1.6449. Now, when you use your Z-stars, you just drop the negative. You don't have to worry about the negative being on there because it comes after a plus or minus symbol. So that's usually the fastest way to do it, is just do 1 minus your confidence interval, divide it by 2, and that's your area, and that's your area to the left. So you're finding so we found the left bound Z star. So we found this left bound Z star right here for our problem was negative 1.6449. The right-hand side would be the positive version, 1.6449. It would be the positive version. Because, again, the reason why it's positive, we got 90% in between, and it's symmetrical. So if the left side is negative 1.644, the other one is the positive on the other side. Now, you could, if you wanted to, how many you have on your calculators? How many have the center option? How many of you have that option that I have on the screen where it says center? All right, so if you wanted to, you could actually just put your confidence interval in there, go down and put center, and what it does when you do that, it actually tells you the left and the right side. Oh, sorry, this is supposed to be at 90%. My bad. That's why I didn't do it. I put 95. So if I go down there and say, okay, I have a 90% confidence interval, and then it's going to tell me, hey, negative 1.6449 on the left and positive 1.6449 on the right. So if you have the newer version, you don't have to worry about doing this 1 minus stuff and dividing it by 2. You can just put in the confidence interval the way it is if you have the newer software on the calculator. Okay? So if you're using my skinny yellow ones, you should be good. All right, so let's get some practice on the 99. Again, I'm going to do it in case you don't have my newer version of the calculator. So I'm going to do an inverse norm. My area is 1 minus 0.99 divided by 2. My mean is 0. My standard deviation is 1. So that would be 0.01 divided by 2, which is 0.005. That is what the area is to the left, 0.005. So second vars down to inverse norm, 0.005. And again, I'm back to doing the left is what I'm doing. And I hit paste. And this tells me that I have a Z star for this one of 2.5758 is what I have. And again, why am I finding these Z stars? Well, if I'm doing the confidence interval by hand formula, I need to calculate what that is because that's the very first thing after the plus minus symbol. That's the Z star right there. So we need that 4-digit number or 5-digit thing. We need that in order to help proceed to get the margin of error. In order to get the margin of error, the Z star, our critical value, is used in that calculation to find out what our margin of error is. Questions so far? All right. I'll let you do the next one if you want to, the 98%. I just want to keep moving. Determine the sample size necessary for estimating a population proportion within a specified margin of error. So here is the formula. It's part of your the confidence interval that I showed above. Again, our confidence interval was p hat plus or minus Z star times, again, p hat times 1 minus p hat over n. Everything after the plus or minus symbol, is considered the margin of error. That's what everything after that, all that component there is the margin of error. And while I have it separated, I want to write one more thing down. So that's margin of error. Margin of error. Sometimes they tell you the standard error. The standard error, or SE, that's just the square root part. That's just the p hat times 1 minus p hat over n. So go ahead and write that down just in case we come across problems where they tell you, hey, the standard error is this. The standard error is the stuff after the star. It's after the T star. It's after the Z star. It's the square root part. That's the standard error. So I just want to sneak that in our notes in case we do it. So they asked us to figure out, okay, if I need to figure out the minimum sample size, so I got to figure out what n is. If they ask me to figure out the sample size, they're going to have to tell me basically what type of confidence interval am I doing. They're going to have to tell me what the margin of error is. And then the p-hat, that's where we have a little choice. If they tell you in the problem that it's based off of some other study that was done, we get to use the p-hat in that study. If they don't tell you a p-hat, then we use like 50%. You know, when would they tell us to use like 50%? I would say if a problem, who's 18 in here? Okay. So did any of you vote in November? Okay. So with this in mind, I know there's a lot of candidates out there you could vote for. However, let's just narrow it down. Did you vote for Trump or not? Your answer to that question is either what? Yes or no. 50-50. Okay? So when you look at situations that they don't tell you that a pilot study was done and a sample proportion is this, look at the phrasing of the problem. If it's pretty much a yes or no kind of answer, then it's 50-50. And 50-50 gives us the 50% for a p-hat, gives us enough wiggle room to where the kind of like the highest it probably could be for a sample. Okay? If they tell us a study was done and the p-hat was 25%, then we're gonna be a little bit lower down in the sample size. But the biggest the sample size could be would be associated with like a 50%. It's like the dead center. That'd be the peak of like a bell-shaped curve. Okay. And so when you're not sure, think about the type of questioning they're doing in the study. If the answer to that, then you use 50%. If they don't give you one. So all we're doing in there is we would do we would back solve is what we would end up doing to do that. Let me scroll through here real quick. I got some examples for us to go through. I'm just trying to see if there's one that we can start with that actually wants us to find the minimum sample size. No. Okay. Oh yeah, they do down here, the death penalty. All right, let's do that one real quick. And then we'll come back and we'll do some of those other ones. All right, so death penalty. In a Gallup poll, 64% of the people polled answered yes to the following question. Are you in favor of the death penalty for a person convicted of murder? The margin of error for the poll was 3%. So margin of error was 3%, which is 0.03. I would always turn percentages into a proportion, make them a decimal, because we needed to make them that way for calculations. They tell us that the poll, they told us p-hat was 64%. So that's 0.64. And then now they say we have a confidence interval of 95%. So our confidence level is 95%. How many people are being surveyed? So what's the N? So this is the way they would phrase it, asking, okay, what's the minimum sample that I need to interview in order for me to have a margin of error of 3% and 64%, based off of 64% of the people answered yes. And I want to do it with a 95% confidence is what I want to go through and do. So as we look at our formula, our margin of error is supposed to be equal to greater than or equal to the Z star times the square root of the p-hat times 1 minus p-hat divided by n. Now, as we start filling in values, we know margin of error is 0.03. I need to come up with a Z star here in a minute using inverse norm. All right, I'm going to find that in a second. Z star we're doing inverse norm for. Now, the square root part. They tell me, based off of a previous poll, a previous study, a pilot study, p-hat was 64%, so I get to use that. If they didn't say that, then I would do 50%. And then now the only letter that's left in the problem is the letter N. Now before we get started, we need to figure out our Z star. So we need to go up and do our inverse norm. Area would be 1 minus 0.95 divided by 2. Our mean is 0. Our standard deviation is 1. And so my area is going to end up being 0.025. And then now if we go to the calculator, we should be getting something around a 1.96 is what we should be getting. Sorry, my calculator is being quirky. So inverse norm, so second vars, inverse norm, 0.025 is my area, leave the rest alone. And I get 1.95996. So when we look at, if we wanted to be super accurate, then we use the 1.95996. If we round to the fourth decimal, it's going to round it to a, sorry, I might press something to click, it moved me up. There we go. So that was 1.95996. So we can use 1.96 if we want to. The more decimals you use, the more accurate you become. So 1.96. That makes that 1.96 makes it easy for me to move stuff around. So now I need to start doing inverse operations. So the first thing I'm going to do is I'm going to divide both sides by the 1.96. So on the left side, and I'm gonna do calculator on a separate calculator so I can keep a big screen here. 0.03 divided by 1.96 is 0.015306124. That is greater than or equal to the square root stuff. 0.64 times 0.36 over n. So let's simplify the top of that fraction inside the square root. So I'm going to copy down the left side. .64 times 0.36. So that's the square root of 0.2304 over n. All right, now I need to do inverse operations. How do I get rid of a square root? Yeah, square it. Sorry, air conditioner was louder than you. So I square both sides. That gets rid of the square root. So then now I have 0.0153061244. Quantity squared. I'm not going to square it because it's going to put it in scientific notation. That is greater than 2304. Now, technically, I would multiply both sides by n and then divide off that stuff squared to get n by itself. When you're doing this type of stuff, the n just trades places with that. So we can say n has got to be greater than or equal to 0.2304 over that big long decimal squared. And so now I just need to work that out. So I'm going to take on my calculator 0.2304, divide it by, and then now that big long decimal, which is in my calculator, so I can actually go up to it, hit enter, tell it to square it. And then just when I get done with hitting out executing that out, I get n is greater than 983.449. So I have to say more than 984. So they got to survey more than 984 people. No matter what your decimal is after the decimal point, you always round up. Yo. I haven't squared it yet. Did you square it? I didn't square it. Before you square it? Oh, 224. Okay. And that may not make us off. Wait, did you finish up the thing?
Not yet.
All right. It shouldn't have us off too much, dear. But thank you. I see. Yeah, I see. Yeah, you know. Now I wrote it down wrong, but since I used the same thing in the calculator, I did use the 224. We're good there. But thank you for catching that. Okay. Because since I didn't type in that long decimal, I used what was in there. My numbers are good. So that's what you're saying. That was supposed to be a 2 there, is what that was supposed to be there. But again, since I left it in there and just told the calculator to square it, it kept everything good. So we should be okay on that part. Again, whenever your decimal is at this stage here, now we always round up. Okay, we always round up. Doesn't matter that we're less than 5. That's what you got to keep in mind. We're always trained to, hey, it was 5, we're up, we round up. If it's below 5, we stay the same. Not in this rule. Okay, we round up to the next whole number. Now, if I used 1.95996, my answer would be a little bit different than that. Okay, so it kind of changes a little bit. Usually, the 2-digit Z-star is acceptable because if you're using the piece of paper, that table that had the Z values on it, you can only go Z-scores out to 2 values. Okay, so I typically have a couple answers down here. If you use the 2 decimals like this, I have that answer down there. Or if you decide to take it out 4 decimals, I have that answer down there. Or I just quickly type it in and say, hey, would you get the same thing? Or did you do your math right? So I usually have those couple things set up. Again, it's a long process to try to find the minimum sample size they need to do that. Okay? But it's just all inverse operations that we learned in algebra skills. Any questions on that one? So I want to get into like a true test thing. There's a whole bunch of more problems on there, so I'm going to sit down while my AP kids, probably next block, they're reviewing for their AP test on means. And then my other AP class, they're doing a multiple choice of free response practice AP exam today. So I'll try to record a bunch of videos, short videos on each of some of the other problems. That way you can click on each video to look at how we solve each of those. But I want to go through and kind of go back to one of those problems and do it in its entirety. So let's see. I'm going to do the FDR later. Let's do the blood one. That would be a good one. So giving blood, a survey of 2,306 adult Americans aged 18 and older conducted by the Harris Interactive found that 417 have donated blood in the past 2 years. Obtain a point estimate for the population proportion of adult aged 18 and older who have donated blood in the past 2 years. All right, so again, point estimate. Our point estimate. They don't tell me a confidence interval, so we have to remember that in this case, it's the p hat. So that is the x divided by the n. So they surveyed 2306, that's my n, and they found that 417, that's my x. So to find my point estimate, I would just do 417 divided by 23. Sorry, my pen's having quirky issues. 2306. So on a little calculator off to the side here, 417 divided by 2306 tells me that my p hat is approximately 1.8130. Verify that the requirements for constructing a confidence interval about P are satisfied. All right, so first off, random. I'm assuming it'd be better if they told us. I'm hoping, my curiosity here, is it a random, it'd be nicer if they told us we had a random sample of 2306. Usually they do. Random sample of 2306 adults. Normal. Remember, our normal clause was n times p times 1 minus p. Are you greater than or equal to 10? So is 2306 times... now, you haven't caught me yet. And this is what happens sometimes when you don't look at an answer and double check. Does it make sense in the context of the problem? What does p hat stand for? What type of value is it? It's a what? It's a proportion, which means it's a percentage. Right now, I have my p hat as 1.8130, 181%. Can we have a percentage above 100? All right, so I just realized and as I looked at my calculator, when I hit the numbers, the 3 didn't register. So mine says mine says 206 is what mine says there for the denominator after the division. Okay? So we need to change my p hat. We need to change that because, again, as I look at my calculator, actually I forgot the 6. I have 230 on there. Somehow I didn't hit the 6. So I need to change this. Go back and say 417 divided by 2306. Hey, that's a lot better. Come on, give me a pen. Come on, pen. There we go. 0.1808. Okay. So 0.1808. And then I need to do 1 minus that. So what is 1 minus that answer in my calculator, which is 0.8192. And is that greater than or equal to 10? So now that becomes a calculator activity. 2306 times 0.1808 times 0.8192. And that gives me 341.544. That is greater than or equal to 10, so we are normal. Again, when I'm dealing with proportions, this whole next week and a half, we're saying, are we greater than or equal to 10 when we multiply the two percentages and the sample size together? Now the next thing, independent. Independent. Is 5 times 2306, is it less than the population? Well, let's look at it. 5 times 2306, 530, so 11,530. Are there more than 11,530 Americans, adult Americans age 18 and older? Yes. All right, so we know that one's okay. We know we're independent. So that means I have met the conditions. I can go ahead and construct the confidence interval. So now I'm ready to do that one prop Z interval. So now I'm ready to do a one prop Z interval. And then, again, when we use that in the calculator, X is equal to 417. N is equal to 2306. And my confidence level, they told us we had 90%, so 0.90. And so now I'm ready for the calculator. stat over to test, down to option A, and then type in my 417, my 2306, 90% confidence interval, so 0.9. And we find that the interval from 0.16765 to 0.19402, that's the interval that captures the true proportion of people that donated blood. So here's my interpretation. I know the bell's getting ready to ring in a minute. We are 90% confident the interval from 0.16765 TO 0.19402 contains the true proportion of adult Americans aged 18 and older who donated blood over the past 2 years. So that would be like the full conclusion statement. We know that we're 90% confident that interval contains anywhere from 16% to 19% contains a true proportion of adults 18 and over that donated blood. So I'll work on videos on some of those other problems. I'll do it maybe two problems on a video, and I'll tag them inside of this and put them right next to it as a hyperlink. Okay, and then I'll also put them on the other places too. Okay. If you have questions or want to work on this in the morning in AFT, please come in and see me. Okay? I'll be glad to work on some of this stuff with you guys in the mornings. Alright. So I'm looking at your all's numbers. A for MTSU is definitely doable. Okay? Definitely doable. Okay? I think for almost everybody in here, being above for MTSU is definitely doable. Okay? If you two ladies, knowing that you scored super well in the last one, if you can keep that same pattern going on the next two tests in the final, you can score nicely above an A for MTSU should happen. Okay. So I know you guys are probably wondering, hey, can I get an A? You know, beach is not an issue. Okay, we get the 5 points. But for MTSU, it's definitely doable. Just keeping the kind of the same pattern you guys are doing on the last couple of tests. Just keep it going. Okay. You know, I figured you would want to work on stuff because I did the same thing for
Nothing. I put a splash of lemonade in my water this morning because I've been very bad, but actually finishing my water.
Yeah.
But it has now gone straight to my bladder.
Oh. That's sad.
I'll be back.
Macy Spicer, report to the annex office. Macy Spicer.
This is 2 munchkins. They're usually here by now, I thought. Hey! Do I want to play Greenbrier? Let me see. Let me email this boy out real quick. Christy Womack.
That doesn't excuse for me. Most of it, I'm gonna to each their own. I'm just saying. Did you like my smile on the face that like your money? I think mine was better. I don't think I did. That'd be more. Maybe Paul on the ninth.
What day is the 9th? Is it Friday? Give me a second.
Keep everything
Plus, 2025 AP exam schedule. Alright, here we go. Alright, here's we got on the 9th. Are you in Italian language? United States history, Chinese language, and macroeconomics. Alright, we're good with it. They do. They have an AP Japanese, an AP Chinese, AP Italian.
None of this. I thought we were
Yes, I'm in all of that.
Yeah. Not.
I speak all of those 20 meters.
Tell me something. Tell me something longer than
They're
7
pouring dirt
words.
on you, but like, you're like.
Longer than 7 words. Alright,
So do me a favor. I sent you out the multiple choice. Don't know how much of that you actually worked on last night. I'll probably assume you're probably done for some of you.
I did every single multiple choice.
Good for you! Woo!
As is one of them.
So if you open up for me to OneNote, to the chapter 10 and 11 pages I sent you in your notes on the multiple choice, let's start going through those. I'll read them and we can answer them as we go. Then there's a couple free responses on there, and we want to get to those, make sure we do those. I started typing up the answer to the Chips Ahoy problem. I think I put on my version of the notes of that page. I think I have the hypothesis test and the confidence interval typed up, all the parts. Like the state plan do conclude, I believe. And I was in the process of doing the difference between the two brands of cookies. And class changes and stuff, and so I didn't do it. So I gotta finish that one up. So I'll share that one with you, the difference, to see you can compare what you did and what I did. We just started confidence interval for proportions in my my dual class, so we're at the stage of scaring them, is where we're at, because they're like, it's like too late now.